We present a computational framework to generate modular congruent tiles that can be put together to create woven structures. We define these woven structures as tile decompositions of a given shell-like volume such that the tiles, when put together, mimic a specific family of fabric weaves known as bi-axial weaves. Bi-axial weaves result from the interspersing of threads in two linearly independent, typically orthogonal, directions that are typically named warp and weft. Another way of representing such weaves is as a binary matrix whose cells determine which thread goes over and under at a specific location. This binary encoding defines a woven structure that can be generated with various techniques. In a previous work, these woven structures are generated by using threads as Voronoi sites, which resulted in long and non-congruent building blocks. Moreover, resulting structures had to change with the fabric pattern. We present a modular approach to define these woven structures which would decrease the cost of creating each structure and make it easy to prototype different configurations. To design our modular tiles, we have set up design conditions. First, the yin-yang condition dictates that the pieces should be decompositions of the fundamental cube unit cell, which makes the pieces closed under a specific symmetry operation. This also suggests that the center of the cube should be shared between the pieces. Second, the saddle condition ensures that the created pieces can share an interlocking interface. Third, the foldability condition enables these pieces to be manufactured from planar materials. Fourth, assembly-disassembly condition is required so that the created pieces should not be geometrically interlocked, preventing disassembly of the pieces. And finally, the connectability condition is required to maintain a surface area between the neighboring tiles so that they can connect through this interface. We choose our fundamental domain to be the cube, which already suits to hold binary encoding of a fabric weave pattern. We have experimented with the Voronoi decomposition of this fundamental domain with the curves defined on the surface of the sphere. This constraint satisfies that the center of the cube is shared amongst the decomposition, which is needed for the congruency. We require that the curves also be applied in a specific symmetry operation, such that the weaves are represented correctly. From these emerging decompositions, we observe a boundary that defines interface between two interlocking pieces. The curve can be parametrized with two parameters in smoothing steps. Parameter space of this curve enables this shape to have different properties. From the control curve, we draw vertices to the center of the cube. This helps us to satisfy the yin-yang and the saddle condition. From the constructed surface, we expand this surface so that it can bisect a fundamental cube domain. The resulting surface is extruded downward to be able to do a Boolean operation with the fundamental cube domain. Finally, a Boolean operation with the cube gives us our final shape. Now, we show the foldability of created shapes with different parameter and smoothing step choices. Our tiles can be generalized to cylindrical surfaces as well. This results in 4 different fundamental pieces. Without the need for congruency, a specific set of tiles can be defined such that the resulting woven structure can represent an arbitrary height field. Thank you for listening. Please refer to our paper for more details.